So this is my first physics lab, which covers a constant velocity. So some of the fundamental principles that I'll be covering is Newton's second law, which states an object in motion will stay in motion unless an external force acts upon it. We'll talk about the equation a little bit into the video. And then another fundamental principle is that an object at constant velocity has a zero net force, and we'll also discuss the position update formula. The purpose of this experiment is to record an object moving at a constant velocity. We're going to calculate that velocity and then put it into a computational model to record the same motion. And then we're going to compare the difference between the computational model and the observed data to see where it differs. The main result concluded that the observed data differed slightly due to human error and unconsidered forces. So this is the introduction in terms of free body diagram. So on the left is when I first released the car. There was a net force pushing the car to the right, as well as a normal force acting up and a gravity force pulling down. So those two forces cancels out and there's a net force to the right. However, once it reaches a constant velocity, that is when I started recording my video. And that free body diagram is shown on the right, where air resistance and friction are ignored, and then normal force going up and gravity force pulling down, and those two forces are canceled out basically. So this is the tracker software analysis that I used. The video started with the car on the left, and then it moved to the right. Every 10 frames, I plotted that point right there on the front of the car, and the entire data set is shown on the left here, and then the graph that it spit out is on the top right. So the track of data that I used, so the observational start time was 0 seconds, the end time was 8.335 seconds, the initial distance was 0.164 meters, final distance was 0.396 meters. And then we can use all this data to find the average velocity, which is change in distance over change in time, which is 0.0278 meters. And all of those two numbers will become significant in the next slide. But one final thing is that the system in this experiment is the car moving at the constant velocity, and then the surroundings is everything else. So here's an introduction to the computational model. So the initial conditions include the initial position, which I said was 0.164, and then the initial velocity vector, which is 0.0278 meters per second. So these are the initial conditions. And then I made the time in the top left, you can see, go to 8.335 seconds. And then I had my delta t 1 second. And then my change in velocity, as you can tell, is 0, 0, 0, because when we have object moving at constant velocity, then there is no change in velocity because there is zero net force. So therefore, we're not changing velocity, so that stays 0. However, we still have to account for a change in position. So we're going to have the ball position plus the average velocity times delta t. And since delta t is 1, that's ignored. But anyway, so the 0.0278 from the last slide, that's still taken into account here. And then we insert it right here. And then we run it and we get this graph. So as you can see on the red is all the data that the computational model spit out, and as you can see, it's very linear, obviously, because it's from a code, whereas the blue is what was observed via tracker. So therefore, there's much more variability due to few reasons. One, the friction was not accounted for. Two, there wasn't a very consistent point on the car that I could use. I tried being as consistent as possible, obviously, however, that's room for human error. Three, there's rounding errors as far as recording the distance. And 4, there is no account for the Y position, so that can change the overall position of the car. As far as discussion and what-if questions, so what if the axis were flipped? So say on the top right picture here, if the Y-axis moved to the right, the only thing this would change would my slope, because it would be negative instead of positive. And is it possible for you to say how many pushes and pulls are added to give a net force of 0? It's not really possible to say. However, we know that the normal and gravity forces cancels out. And we know that the car does have a low amount of kinetic friction, the car has low amount of friction forces because it's on that track. And however, we still didn't take into account air resistance and that low amount of friction. So all of these are factors that could affect their accuracy.